going to explain about production of acetone in terms of principle of chemical engineering. Basically, acetone or propane is an organic compound which used in wide range industries. And then, for your information, production of acetone actually required a lot of understanding in principal chemical engineering and also fluid mechanics. This is to make a sustainable and high efficiency system. And as you know, the chemical equation for production of acetone is process of dehydrogenation of isopropanol, and then we'll produce an acetone and also hydrogen as our co-product. In this case study, we choose reactor as our reactive system and heater as our non-reactive system. The function of heater and the function of reactor is different. In this case study, the function of heater is used to increase the temperature of the chemical substance which next to send the reactor to undergo next process. And then the function of reactor is to change the isopropanol to acetone, and also we will have hydrogen as our co-product. Hi, so here is the explanation in terms of fluid mechanics. So basically, fluid mechanics play a vital role in designing the movement of reactant and product with associated equipment, because proper fluid flow help ensuring the uniform mixing, heat exchanging, and also effective separation. In process flow diagram, or also PFD, must consider heat transfer efficiency, pressure drop, and energy consumption. Downstream separation process, whether it is distillation or condensation, and many more. A well-designed fluid transport system, or we call it as pipeline, minimize energy losses, enhance reaction efficiency, and help improving overall process safety and yield. By applying this consideration, we can produce a high efficiency system, and also we can reduce waste as much as possible.
Hi, my name is Jade. As you can see in this slide is the chosen process flow diagram that we find in the internet, and to the right hand side is actually the process flow diagram that we made in the Symmetry apps for this system production of acetone. Based on the assignment that we have to choose one non-reactive system and one reactive system. So for the non-reactive system, we actually choose heater as one of our non-heater system throughout the production of acetone. And for the reactive system, that we calculate is the reactor that undergoes dehydrogenation, which is one of the reactive column. So for our mass balance for non-reactive system is actually very easy and clear. As you can see, isopropanol it's actually 1000 kg per hour, and for the output also will be the same. And water input will be 500 kg per hour, and output will also be the same. So we calculate the mass fraction, which is isopropanol is 1000 over 1500, and we got 0.6667. And for the isopropanol, output also will be the same, which is 0.6667. In this slide, we will be performing mole fraction and also total mole fraction for non-reactive system by using the formula above, which is the mole fraction formula. Then we will get the isopropanol is the 16.6667 kilomole per hour, and for our water is 27.7778 kilomole per hour. And the below fraction is actually the mole fraction for each compound.
Hi, my name is Nurin Darusha, and I'm going to explain about reactive system where a chemical reaction takes place. To calculate the mass balance for this system, we assume that only 84% of isopropyl alcohol is converted to produce acetone. First, we take the mass flow rate at the outlet of the non-reactive system as the inlet value for the reactive system, because both systems are positioned next to each other. Next, to calculate the mass balance for the reactive system, we first convert the mass flow rate that we obtain to the molar flow rate. Then we apply the formula mole flow rate out equal to mole flow rate in plus changes, where the changes refer to the consumption or the generation of the component. As you can see, the water flow rate remain unchanged because water only acts as the heat controller to absorb excess heat and prevent overheating. Then after obtain all the value, adding up all the molar flow rate, and we get the total of 48.4445 kilomole per hour. After that, we calculate the mole fraction at the outlet for each component using the same method as in the non-reactive. Then we convert the molar flow rate to the mass flow rate by multiplying it with the molecular weight of each component. And finally, we determine the mass fraction of each component using the same method as the mole fraction.
In order to find the energy balance for non-reactive system for our heater, we will be using Q equals to N out H out minus N in H in. And we assume that the conversion is 100% into vapor after the vaporizer, means that the IP air and water both of them will be in gas phase. As you can see, our water is in vapor 100 degrees Celsius and 1 atm. It changed to 325 degrees Celsius. We perform integration in order to get our H1. And to change the pressure 1 atm to 2 atm, we use the equation which is V theta P. But this is it will be in the gas phase, so the pressure difference will be less than 5 atm, so it will consider as 0. Then we will be getting the answer. For the IP air, we set the reference state as vapor 1 atm 319.39 Kelvin, and for the outlet will be 598.15 Kelvin. Pressure will be 2 atm and in vapor state. In order to find the outlet, we have to change the temperature from 319.39 to 598.15 Kelvin by using the integration of Cp. After that, we will change our pressure, which is from 1 atm to 2 atm, that we consider as 0 because it's in gas phase. By using the Q equals to N out H out minus N in H in, we will be getting 94.7123 kJ per second for our non-reactive system.
For energy balance of the reactive system, we take the reference state as a vapor at 25 degrees Celsius and 1 atm. The inlet condition of the system are a temperature of 325 degrees Celsius, a pressure of 2 atm, and a vapor state. Meanwhile, the outlet condition are a temperature of 350 degrees Celsius, a pressure of 1 atm, and also a vapor state. To calculate the energy balance for the system, we use the same formula as in the non-reactive system, but with some additional term, which are the extent of direction and also the standard heat of reaction. Next, we calculate the specific enthalpy for each component at both inlet and outlet. To do this, we must perform a hypothetical process path where we adjust the temperature, pressure, state from the reference state to match with the actual stream's condition. For the inlet component, which is contain H1 and H2, we calculate the temperature change using the specific heat capacity, or known as Cp, for each component, which is given in table B2. However, the temperature for H1 must be converted to Kelvin first. Additionally, the pressure change for both H1 and H2 is considered negligible or equal to 0 because the pressure variation is less than 5 atm. By using the same method, we calculate the specific enthalpy for the outlet stream. And finally, we apply the formula mentioned at the beginning of the slide, which is delta H equal to extent of reaction multiplied by standard heat of reaction plus formula for non-reactive energy balance. By substituting all the values, the energy produced is 1,724,905 kilojoule per hour, which is equivalent to 479.141 kilojoule per second.
So hi, my name is Demet Rocky. On this page on the left side, we have our pipelines, materials, diameters, lengths, and fittings. So we use stainless steel as our material as it doesn't react with chemical reaction and is suitable for our custom production. For diameters, fittings, and length, we got from our references from the Google. And on the right side, we calculate Q, which is equal to mass flow rate over density. We got our mass flow rate from the PCE parts. And then we have our custom viscosity at 20 Celsius from Google too, from our references, which is 0.32 multiplied by 10 power of -3. for the stainless steel constant, we have 0.002 multiplied by 10 power of negative 32. This is for our next calculation. So here is our two of example from our calculation. We have 3 in total. So for the first part, we find the velocity using formula Q over A, and after we got the velocity, we can calculate the Reynolds number using formula density multiplied by velocity multiplied by diameter over the viscosity. So after we got the Reynolds number, we can conclude that our pipeline is turbulence flow. So using the turbulence flow friction factor formula, we calculate the friction factor, and after we got the friction factor, we calculate the friction loss, total friction loss in the pipeline. So after we got the friction, before that, we use the 4 multiplied by the length by the friction factor, and then we divide by the diameter plus KE, KC, and KF, and then multiply again with the velocity, the power of 2 over 2. So after we get the friction loss, total friction loss, we can calculate the pressure drop using the formula friction loss multiplied by the density, and then we get the total for our pressure drop. So this is our summary of pressure drop that we calculate from the previous part, the 3 of our pipeline, main pipeline. So for the pipeline 7, which is condenser to flash drum, we have 84.23 pressure drop in unit PA, Pascal. And then for pipeline 9 and 13, from flash drum to acetone column, we have our pressure drop which is 124.49. And for pipeline 9 and 13, we have 141.59 PA, Pascal.
We go further to the delivery strategy for the pipeline system. We choose for the IPA column to feed drum as our storage tank. The transportation involved can produce the effect of contamination and leaks that need further handled to avoid damaging the equipment and contaminating the environment. To prevent this, we have selected the centrifugal pump as our pump since it has high efficiency to handle the acetone, which is the low viscosity liquid, and we also relies on the flow rate and head loss which obtained from the friction loss, considering the fluid mechanics principle including Bernoulli and energy equation. The whole pipeline consists of standard T flow through run and 3 of 90° long radius elbow with elevation approximately 3 meters from the top of the IPA column. Next, we estimate the pump power by obtaining it from the energy equation with calculated mass flow rate and velocity. We also consider the constant for the pipe fittings and the length of 40 meters. As for our pipe and storage tank description, first we ensure that the description complies with the material and the safety compatibility, as the IPA column separates the acetone from the isopropyl that produce the high purity of acetone at the top of the column. Since we use centrifugal pump, the pump can compensate the losses from the pipe fittings and ensure the adequate fluid delivery. The material used for the pipe is stainless steel with an FUC lining with the diameter of 43.6 mm, and the last one, the dimension of storage tank. We use the speed flow with pressure vacuum vent with the capacity of the 94.39 m3 in 8 hours per 70 capacity with the diameter of 4.3111 meter and the height of 6.4667 meter.
In a nutshell, I can say that we are exposed to the hydrogenation process. This is because of the conversion of the isopropyl to acetone requires a dehydrogenation process. And also, we learn the catalyst help in decreasing energy. The improvement of catalyst and the energy recovery also help enhancing the sustainability and efficiency of production. Third, material, mass, and energy balance, providing a framework to quantify flows and energy requirement. system as Flash and Scrabble highlights the importance of advanced separation techniques in the system. And I can say that overall, production of acetone is a well-integrated process that showcases the relation in between principle of chemical engineering and fluid mechanics.